So today we are going to start with quadratic story problems. And here's what I'm going to say. Today we're just kind of getting our feet wet before tomorrow we jump in a little bit more. We want to make sure we sort of have the basic ideas and concepts. This worksheet I do have posted on Canvas. You can sort of make the decision of if you want to write down every word or not as we go through. But I do want to show you a little bit of information before we even start looking at the story problem. And that's sort of the piece of just transitioning from a random graph that we can make that represents an equation to what those pieces of the graph actually are telling us. Just like we did with linear functions, right? And we were doing relating graphs to events. And if I was standing at the door, then I was 0 feet away from the door if that was my starting point, right? And as I walked away, that was increasing. What do all of those pieces tell us? So the reality is that when we graph a quadratic, right, we might get a U-shaped graph, and that's fine, but there's only certain pieces of it that are actually reasonable, right? We talked about that same thing with linear functions. If our x-axis is time, okay, it's not going to be reasonable to have negative time. So all of this space over here becomes unimportant. And if our y-axis is maybe height or distance or length, okay, we can't have negative of that either. So none of this is going to be reasonable either. And just like we saw when we were relating graphs to events, the only really reasonable or important part that we might be looking at is what's in quadrant 1, right? We have 4 quadrants. This is quadrant 1, 2, 3, and 4. Okay, so if we are just looking at quadrant 1, we might not see as much information. Oh, I don't need to draw that big of a picture, right? So in quadrant 1, right, we have more stuff of the axis sort of happening over here, but right, 2, 3, and 4, these quadrants aren't really important, and we might only see this piece over here. And so now while there's part of a quadratic happening over here, the important part is what's happening when we are in this quadrant. Okay, so for example, the first story problem that we are going to look at today says, suppose a football player kicks a ball and gives it an initial upward velocity of 47 feet per second. Right now you're probably like, oh my gosh, Mrs. McKinney, I don't know what those words are. Just bear with me. Like I said, we're just getting our feet a little bit wet today. The starting height of the football is 3 feet. And we represent this with, look, it's so nice to us, it tells us all of that information that it just gave us is represented with this equation. Now, we are going to talk more about, as we go further into this, that negative 16 is gravitational pull, right? When something goes up, it comes down because of gravity. The 47 in front of the x is going to be representing our feet per second, and our ending value, our constant, is always our starting height. Okay, but it gives you the equation for you. You don't have to write it. You don't have to come up with it. It's the great thing about that. Okay, if no one catches the ball, when will it hit the ground? And the nice thing about quadratics is that our graph kind of looks like exactly what's happening. So we have a person. You know, I draw great pictures. Okay, and they have a football. Oh, that's even better. Okay, and when they kick it, right, they first make contact with the football right here. And so the football starts going up, and then because of gravity, it starts coming down. Okay, so this problem wants to know if no one catches the ball, when will it hit the ground? Well, if we look at this, right, in the air, 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 here, over here is where it hits the ground. Okay, and if we remember, that's one of our roots or zeros. That's an x-intercept. And x-intercepts are the same thing as solutions. So what it's really asking us to do is to just solve the quadratic. So when we're trying to find this spot on the graph right here, we're just solving. And we can do that with the quadratic formula. We can do that with completing the square. We can do that with factoring. I know a couple of you, Olivia, are going to be using the quadratic formula no matter what, which is totally fine. So that's just completely up to you. You can decide. So what this is really saying to us is solve this quadratic? Well, it's already set equal to 0. So to solve this quadratic, a doesn't equal 1. Most of you are going to want to go with the quadratic formula because of that negative 16. So here we go. A equals negative 16. B equals 47. C equals 3. So at this point, we should know the quadratic formula. It is negative b, right? Plus or minus. We have b squared minus 4 times a times c all over 2 times a. Use a calculator. I cannot stress this enough to you. Some of you are missing problems on the test simply because you're just not letting yourself use the technology you have available. So now we're just going to look underneath the square root and type in exactly what we see. Notice I am not typing in the square root symbol. Uh-oh, what did I type in wrong? A multiplication symbol. Oh, there we go. Okay, so there we go. So we get 2401. So we have negative 47 plus or minus the square root of 2401 all over negative 32. Now, just like we talked about with our area, length, and width problems, right? If we take the square root, right? So we're going to check the square root of 2401. And while this one does give us a perfect square, same thing as before. We are ready for a label in this story problem. So no matter what, we want to take the square root. We might just end up with a decimal approximation. Okay, so the square root is 49. So now we have negative 47 plus or minus 49 all over negative 32. And just like solving with the quadratic formula, we now need to look at both options. Negative 47 plus 49 over negative 32. And negative 47 minus 49 all over negative 32. Now remember, if you're using a calculator, again, you have to do negative 47 plus 49 equals divided by negative 32. Okay, so that gives us negative 0.0625. And we need negative 47 minus 49 equals divided by negative 32, which gives us 3. Okay, so we have 2 answers here. Again, just like length and width, we are talking about when. Okay, so we have seconds as our label up here. Can we have negative 0.0625 seconds? Well, no. That's not a reasonable answer. This isn't reasonable. Okay, so while mathematically it works, it's representing this point back here, right? It's representing our other x-intercept, but none of that is part of the reasonable portion of the graph. So we're not going to use that one. Okay, so then that means our answer is going to be 3. That answers, right? If no one catches the ball, when will it hit the ground? It will hit the ground after 3 seconds. No plugging back in, no nothing else, 3 seconds. Okay, so really, as long as you know the quadratic formula, you're pretty set on this. So if we look at number 2, a child is now tossing a ball. It has a starting velocity of 10 feet per second, and it's from a height of 3 feet. We want to know when will the ball hit the ground based on this equation. Okay, so we're looking for where it hits the ground, which is this space over here, which means we need an x-intercept or a solution. So we are going to start solving this. So a equals negative 16, b is 10, c equals 3. So that gives us negative 10 plus or minus 10 squared minus 4 times a times c all over 2a. So again, let your calculator help you. So we'll type in just underneath the square root, and we get 292. Okay, so now on this one, let's take the square root of 292, and we do not get a perfect square. But we're gonna have to do a decimal approximation because we don't talk about time as a number with the square root. We just don't do it, right? So decimal approximation, just like we said before, let's go to the nearest hundredth. So we'll do negative 10 plus or minus 17.09 all over negative 32. And now we're going to have to calculate both options. Negative 10 plus 17.09 over negative 32 and negative 10 minus 17.09 over negative 32. So on our top one, we get negative 0.22. And again, I'm rounding there to the nearest hundredth. And here we get 0.85 when I round to the nearest hundredth. Okay, again, we have feet per second. Time cannot be negative. So that's not a reasonable domain. So we get an answer of 0.85 seconds. Now, this is about 1 second, but right, doesn't that kind of make sense if we have a child throwing a ball? It's just gonna kind of plop to the ground, right? We're not going way up in the air. We're probably getting more of a parabola that's just doing this and falling straight down, right? So it seems reasonable that our time length isn't very long. Now, knowing all of that info, let's just take this one step further. And let's say, okay, now I'm going to tell you what our formula is for dealing with vertical motion, which is all these problems. Okay, so a man is standing on a high dive at his local pool, which has a height of 24 feet above the water. If he jumps up off of the high dive with a starting velocity of 6 feet per second, how long will it take for him to reach the water if we represent this motion with? Okay, so here's our formula. H equals negative 16t squared. Usually we do this as t because t is time. Okay, plus v. So v is going to be our velocity. So he's doing that at 6 feet per second. So we're going to plug in 6 for v. And c is going to be our starting height. So our starting height here is going to be 24. Okay, now, assuming that the water isn't like buried in a deep hole or anything like that, right? The pool is, but the top height of the water is basically ground level, right? Where he hits the pool is going to be where we have a solution, where we have an x-intercept, right? The pool water's here. So where he hits it is our x-intercept. So now all we need to do is solve this. Now, we have this catch of, okay, but I don't have a 0 over here. Well, the height of the water is at 0, right? The water isn't off the ground, the person is. So our h is going to be 0 when he reaches it. The height will be 0. And so now this is something that looks just like before, and we can solve it. So we have a equals negative 16, b equals 6, c equals 24. And here we go into the quadratic formula, right? If you don't know it at this point, pull that out, set it right next to you, right? It's not going away. A times c all over 2a. So we'll get that number underneath the square root. Oh, guys, this is b. Sorry, this is a 6. So 6 squared minus 4 times negative 16 times 24. So we'll get 1572 underneath the square root. All over negative 32. So now let's take the square root of that. Okay, again, not a perfect number, so we're going to round. So that will give us negative 6 plus or minus 39.65. And now we're going to calculate both options. Okay, so we'll have a negative 6 plus 39.65 and a negative 6 minus 39.65. So on top, that will give us a negative 1.05. On bottom, we will get 1.43 if we round. Time cannot be negative, So about 1.5 seconds.